So, again, Kayla's going to try to put, who can recognize this? Elsa, yes. This way, I'm not sure how clear it's going to be on the, video camera. And who can recognize this? Boat. It may or may not be the pirate ship from the Lego movie. It seems a little bit happy for that. But, so this will try to keep me central over here, so none of the proofs in this class can be too long. Okay? The difficulty is trying to make sure it stays in focus. All right. So there's a lot to do this semester. One of the biggest things is changing your advantage of how you view mathematics. So I am not a trained applied mathematician. I just impersonate one on YouTube and in the lecture room. Okay? I have done a lot of applied math problems. And so, again, you're going to get a slightly biased view of what applied mathematics might look like. It's the best I can do. Okay? So what I want to do today is I want to revisit some things that you've hopefully seen multiple times in your life. But I want to do them from a slightly different perspective. So what is the main emphasis we have in this class? Efficiency, right? Is it okay to solve a problem in 10 years? No. I give you plenty of time on exams. I actually even give you extra time to sleep on exams. And you don't have to know ahead of time when you're going to be sleeping. If you fall asleep during the exam, that's fine. That counts as your sleeping time. But you cannot wait 10 years for an answer to come in. And so this is one of the biggest changes in perspective. You're no longer going for an exact solution. How many of you have taken abstract algebra? And the record will show my hand is down. So in abstract algebra, you start learning about polynomials and properties of them. If you continue to Galois theory, you start talking about these wonderful results about when can you write down closed form expressions for the roots in terms of the coefficients of the polynomial. And it turns out only if the degree is 4 or smaller. Once the degree is 5 or larger for general polynomial, we can no longer write down the roots in closed form. Fine. We can often have these iterative procedures that can get us the roots to 32 decimal places in a matter of moments. And for all practical purposes, that's enough. If not, run it a little bit longer, get 64, get 128. And so this is a very new perspective, that it's okay if we don't have the exact answer. To some extent, you've had this all your life. Can somebody tell me what the sine of pi fourths is? Oh dear, it's going to be a long semester. The sine of pi fourths, or sine of 45 degrees if you prefer. Square root of 2 over 2. What's the square root of 2? Yes? Okay, continue. That's it, 1.414, 1.4142. So we write down something like square root of 2, but this is just mathematical notation. And if we actually want to work with it, what is the square root of 2? So there's a lot of things you've been using all your life where you haven't even realized that you've written down something you think it's exact, but it's not. So we have ways to calculate these things. What I want to do is Horner's algorithm. How many of you have seen Horner's algorithm before for evaluating polynomials? All right, if you have seen this, you are not allowed to play the game. Okay, so let's say I give you a polynomial f of x is an x to the n plus an minus 1 x to the n minus 1 plus a1x plus a0. So I have some general polynomial. Can someone tell me a procedure to evaluate this polynomial at 2? I do not care how efficient it is. I just want some procedure to evaluate this function at 2. Other than I go to my calculator, I go to Mathematica. How would you evaluate this at 2? Plug in 2. Okay, so how do I plug in 2?
Substitute 2 for x.
Substitute 2 for x and do it term by term by term by term. Okay, so f of 2 is an, 2 to the n plus an minus 1, 2 to the n minus 1 plus a1 times 2 plus a0. For those of you who are still trying to decide if you want to take this class, I promise it will get a little bit more involved in this. Okay? Let's calculate how expensive this is, right? This is what we're supposed to be doing. You do not do anything in life anymore without seeing how expensive is this. Which do you think is the more expensive operation, multiplication or addition? Multiplication, right? Addition is so cheap relative to multiplication, we will effectively call addition free. All right, it's like the Ginsu knives, okay? You get addition for free when you do sufficiently many multiplications. How many multiplications does it take to compute this term? I'm sorry? N multiplications. How many here? And how many here? 0. So the number of multiplications is 0 plus 1 plus n. All right. So how many multiplications does this cost? Who remembers the sum? N times n plus 1 over 2. How can we prove this? Yes?
By pairing them?
By pairing them. So this is the method Gauss used, is if you write the numbers backwards, n minus 1, you see that each pair adds up to n. I have n plus 1 pairs. I've double counted everything. So the sum is n times n plus 1 over 2. So if I want to get a sense of how expensive is this, the cost of this operation of evaluating the polynomial this way is going to be essentially n squared. Okay, yeah, there's a constant over 2, but roughly the expense of this operation, this polynomial evaluation, is it's an order n squared algorithm. How many additions do we have? You know, how many additions do we need to evaluate this? N. So in fact, even if we worried about addition, which we don't, I'm allowed to discriminate like this, the number of additions is far fewer when n is large than the number of multiplications. And addition is far easier to do than multiplication. Really, the bottleneck is the multiplications. All right. One of the things I like about this problem is if you don't remember the sum of this, or if you don't remember how to get this sum, that's okay. We can talk about estimating. I want to know just roughly how expensive is this. So I want an estimate for this sum. And this is one of the big things, one of the big themes of this class, is if I give you a problem, can you estimate its complexity? And the importance of this is getting some idea of, is it worth waiting for? Is this going to be solved in a reasonable amount of time? So I want a bound 0 plus 1 plus n. And I want an upper bound, and I want a lower bound. Usually there's one smartass in the class who speaks up at this point and gives me a lower bound. Anybody want to volunteer today? I'm sorry? Wow, I think you've just set the record for best smartass answer in the history of my career at Williams. All right.
I have an upper bound.
I don't even know what you're going to say. Oh, sorry. Oh, sorry, you didn't show it enough here. Sorry. Yeah, I'll try higher. There you go. Okay. All right, so, oh, wow, we lost the camera. So, hello. Okay, so, all right, so we have the negative infinity, and I was assuming you were going to say positive infinity. Yeah, we broke the camera on this one. All right. So what else can we do? We've got negative infinity, we've got positive infinity. Can we do anything a little bit better? Yes?
N squared would be a good upper bound?
N squared would be a good upper bound. Why is n squared a good upper bound?
Because you have n terms.
We have n terms. Each term is at most n. So as an upper bound, we have n times n. Because we know the answer, we know that this is actually a good upper bound. It's of the right order of magnitude. I saw a hand in the back. Do you have a lower bound?
Yeah.
Yes.
N.
Okay, so lower bound of n. So you are infinitely better than the person 2 seats in front of you. Right? But is your answer a good answer? All questions are good, no questions are stupid, but answers I can distinguish. Is this a good lower bound? Yes or no? Does this describe the true behavior of the complexity? Is n a good approximation for n squared over 2? No. So this is not sufficient for lower bound. We're missing too much information. It is infinitely better than what was before. And it's much better than 1, which a lot of people give, or 0. But we can do better than n. What kind of lower bound can we get that's better than n? So we got n squared by saying I have n terms and each term is at most n. We're getting n by saying I have n, okay, I guess n plus 1 terms. Oh, we don't have to worry about the 0. I have n terms. Each term is at most 1. Well, the problem is that 1 is too different from n in terms of size for this to be good.
Say like n squared over 2.
Okay, why n squared over 2?
Well, if you use the average value.
Okay, so one thing is if I try to do something like the average value, I will get that. I've got to be a little careful then about what's going on at exactly the center. So you've actually overshot and you've been a little bit too clever. I want a little bit less clever. It's a good answer. Too good. So the difficulty for the lower bound was using the entire range. If we go all the way down to 1, there's too much of a change in magnitude from 1 to n. About how far down should I go? Halfway. So if I go down n halves, how many terms do I have? N over 2 terms, and each term is at least n over 2. So I actually get n squared over 4 from n halves terms, each of size n over 2. This is a much better lower bound. So now I've got n squared over 4. I have n squared. So now I'm somewhere between 1 and 1/4 for the coefficient. I have the right order of magnitude. And you can actually play a lot of games. This is called dyadic decomposition, breaking the region in half, estimating on each one. You can keep iterating. You can keep doing more divisions. And this will actually converge in the limit and give you the right n squared over 2. It's not worth going through all that steps. But what I want you to see here is just this very simple calculation. We can get a really good sense of its size by very simple arguments. And for a lot of purposes, we don't really care too much. Is it a factor of 1/2, 1/4, or 1? We care how does it grow with n. Okay. There are many other ways to evaluate this. Okay. So this was brute force. So Horner's algorithm is the following. So for Horner, we write it as follows. F of x is anx plus an minus 1 times x plus an minus 2 times x plus dot dot dot. So what we're doing is we're grouping things with parentheses. So for example, if I give you f of x is 4x cubed plus 7x squared minus 2x plus 8, I would write this as 4x plus 7 times x minus 2 times x plus 8. From a theoretical mathematician's perspective, does this matter at all? In any other math class you were taking, would this matter? No. From a practical perspective, however, this is a much better way to do the calculation. How many multiplications do we have? And your answer can be within 1. N. So the number of multiplications is approximately n. Maybe it's n minus 1, maybe it's n plus 1, I don't care. It's on the order of n. How many additions? Again, approximately how many additions do I have? Yes. Also n. So I'm not really saving anything from the brute force approach when I do it this way, in terms of addition. But in terms of multiplication, it's a square root savings. So rather than doing, say, n equals 1,000, rather than doing 1,000,000 operations, I'm doing something on the order of 1,000 operations. The savings is astronomical. Okay? So this is Horner's algorithm. And so right now, for the beginning of the semester, what I want to do is I want to kind of ease you in and give you a time to do some reading in the book. So build up a strategic reserve. Read ahead in the linear algebra book. Read ahead in my notes so you get this done. I want you to have some time to review your linear algebra, get your linear algebra up to speed. If you are having issues, talk to me or talk to the TA. We're very close to having a TA for this class. Okay? Talk to each other. I want to use the first week or so to just review some ideas that I hope you've seen before. I'm pretty sure everybody's evaluated polynomials at some point in their life. And talk about how we can review this material from a new perspective. One of the most important applications of this is in fractals. And so in fractals, you want to evaluate things very quickly, very efficiently. And a lot of fractals is from polynomial evaluation, where you keep evaluating again and again and again and again. And the savings here, it just propagates enormously through the system. And so in terms of making certain calculations practical, this is the way to go. Right. One of the things I want you to get out of this class is to ask questions. So the question was, I give you a polynomial. What is the best way to evaluate that polynomial? So this is not a proof that this is the best way. It seems likely that this is the best. Why do you think you can't do too much better than this?
Because you can't have a bound lower than n for the number of multiplications or additions, because you need to do each term.
So we need to do something with each term. And so it seems reasonable to believe we can't do better than n. So this is a real danger. When I was in high school, one of my physics textbooks had the following quote, which has stuck with me all these years later. It was a small section on special relativity, obviously not too much of the advanced theory, just trying to explain what special relativity is to high school students. And the line is something along the following. These results may seem counterintuitive at first, but you have to remember most people don't have experience traveling at 3/4 the speed of light. I like the word most. I don't really know anyone who has had experience traveling anywhere near 3/4 the speed of light. But what you see is you see a small regime of the world, and you try to extrapolate that to everything else. And that's very dangerous. There's a great quote by Mark Twain, a cat that jumps on a hot stove will never jump on a hot stove again, but will also never jump on a cold one. For each experience in life, draw only the lesson you're supposed to. So this idea that we need n terms, there should somehow be a cost of n multiplications. Maybe that's true in general. Could there be some special polynomials that might be easier to evaluate?
Yeah, if we had like a linear term to some power, we could do it in y.
So if we have a linear term, we can actually do much better. And so Horner's algorithm is, I think, but I'm not positive, one of the best things you can do in general. But frequently you might be fortunate enough to have something of a special form where you actually have additional structure. So this is called fast multiplication. Let's let f of x equal x to the n. So naively, n minus 1 multiplications. Right? And so the example I always use is x to the 100 is x times x times x. There's a much better way to do this. And the way is through binary expansions. X times x is x squared. X squared times x squared is x to the 4th. X to the 4th, x to the 4th is x to the 8th. X to the 8th, x to the 8th is x to the 16. X to the 16, x to the 16 is x to the 32. X to the 32, x to the 32 is x to the 64. Damn it, I ran out of blackboard space. Is that a problem? No, why is it not a problem? I'm sorry?
You don't want to go any further.
Yeah, I don't want to go any further. I only have to get up to x to 100. The next term is going to be... Right, you should have all played 2048 by now. You should know these powers of 2 by heart. Okay? So binary expansions. I can write x to the 100 in binary as x to the 64 times x to the 32 times x to the 4. And so I only need this one, and this one. So how many multiplications does it cost? 1, 2, 3, 4, 5, 6. Then I have to multiply by this 7, multiply by this by 8. I can do it in 8 multiplications. Is this better than brute force? Okay. Why might this be worse than brute force? I will eventually learn where to stand. Yes?
What if you, like x to the 32nd, what if you lost too much, what if you couldn't store it that much?
Well, okay, so you're on the right track, but if I can't store x to the 32, then there's no way I'm going to be able to multiply up to x to the 100. So you're on the right track that there's a storage problem. But the storage problem is not in this calculation. Yes?
You have to remember the previous term.
I have to remember all the previous terms. Now, the number of terms I need to remember, if you count them, I have to remember on the order of the logarithm of the exponent. So the number of terms I need to remember is smaller, but this does use a lot more memory. Whereas if I do the brute force multiplication like this, I just have a counter. For n goes from 1 to n, you replace temp equals temp times x and just cycle through like that. So the storage cost is much less for the brute force than this. You can actually decrease the storage cost here enormously. Start off with 1, and then x times x is x squared. And so what I'm going to do is I'll save the pair 1 and x squared. I now multiply x squared by x squared and I get x to the 4th. I'll save that. And now I multiply 1 by x to the 4th because that's one of the things in my expansion. The next step, I multiply x to the 4th by x to the 4th, I get x to the 8th. I store that, and I don't change the x to the 4th because x to the 8th doesn't occur in the expansion. I keep going down like this. X to the 8th times x to the 8th is x to the 16th. I don't need to store that. I keep this as x to the 4th. The next step, I'll get x to the 32. I do need to store that, so now this becomes x to the 36. The next one, I'll get x to the 64, and I multiply that in here, and I get x to the 100. And so by doing it like this, I cut down my storage cost enormously. This is applied mathematics. This is a huge part of it. And you either like stuff like this or you don't. From a theoretical point of view, is any of this important? No, the theory of multiplication does not depend on doing tricks like this. We can do things by brute force. But if we want to get answers in a reasonable amount of time, this is not going to work. Okay? So this is what we need to be thinking throughout the whole semester. And if you want to go into fields like this, beyond. How can I arrange my computations in such a way that I can work with the hardware restrictions I have? That I can work with the storage constraints, the computational constraints. I might have to worry about things overflowing. And in fact, maybe x to the 100 is so large that I can't work with it. And you have to find new data types or new ways to save information. And maybe you start breaking things up. And once I reach a certain point, I have maybe some kind of storage marker, and then I build things back up later. So there's a lot of issues in just doing a calculation like this. Okay, so this is fast multiplication. Some of you have taken, I think, a cryptography course with me a while back, or some of you might have taken protecting information. If you've ever seen RSA, which for years was the gold standard of cryptography, one of the reasons RSA was so powerful was that it was easy to use. It was easy to encrypt and decrypt. You don't want to spend 5 years, encrypting a message, transmitting it, and then another 5 years for the person to decrypt. You want to be able to do things quickly. And one of the keys behind RSA is this idea of fast multiplication. This ability to do certain calculations much faster than you would expect. Okay, any questions about fast multiplication? All right, what I want to do now is I want to switch to a topic in linear algebra that I'm assuming you have not seen. I'm just curious, how many of you have seen the Strassen algorithm? It's tough for me to say excellent. So, everybody has their own, pet peeves about what should or shouldn't be taught. To me, one of the big themes of linear algebra is doing calculations efficiently. A huge part of linear algebra is choosing the basis that makes the calculations easiest. How many of you remember conic sections from high school? I heard a few. It's hard not to groan when you remember what you were doing in high school. If you use your imagination, that's an ellipse. Okay? If I give you an ellipse like this, can you write down the equation? I'll tell you the intercepts. Can you write down the equation of the ellipse? So this is going to be just x over a squared plus y over b squared equals 1. This is the equation of an ellipse. What if I give you an ellipse like this? How many of you remember how to find the equation of an ellipse like this? This one picture illustrates the main idea of linear algebra. The way you solve something like this, right, you lean back like this. What happens if I lean back like this? Yeah, then it becomes aligned perfectly. So if I call this, the xy axis, if I call this the uv axis, in the uv basis, it's very easy to write down the equation of the ellipse. And then I just have a rotation by theta degrees to get from the xy basis to the uv basis. This is what linear algebra is all about. Choose the basis that is most appropriate for the problem you're looking at. And different bases, different problems, different bases. This quickly leads to the need to calculate matrices, or oftentimes products of matrices. And so one question becomes, how expensive is it to find the product of matrices? So, we are going to need to use linear algebra when we do linear programming. And so I'm trying to review linear algebra in a fun way rather than just going through and reviewing everything you've seen. So let's say A is n by n, B is n by n, C is A times B. So here's A, here's B, and here's C. And I want to calculate this product. How expensive is it to calculate Cij? How would I calculate Cij? Yes? So I take the ith row of A, the jth column, and I take the dot product. So it's ai1 b1j plus ai2 b2j plus dot 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 plus ain b and j. How expensive is this calculation? I'm sorry?
Pretty expensive.
Pretty expensive. Quantify that. What's the cost? So whenever you're asking the cost, yes? And additions and then multiplications, right? Right. You're used to thinking of things in terms of dollars or euros, right? We measure things here right now in terms of multiplications and additions. The additions, again, are essentially free. I don't really care about the additions. Now, there's a little caveat. If I have to do a quadrillion additions and one multiplication, maybe I start to worry a little bit about the additions. But for the most part, if the numbers are big, the multiplications dominate the additions. So the cost is n multiplications, n additions. Is that correct? No, what is it? N minus 1. We have a little bit of a savings. Right? N minus 1 additions to get Cij. Right. Is it a big deal to write n versus n minus 1? No, because n is arbitrary and we think of n going to infinity. If n was small, that could actually make a huge difference. And we will see later today that that makes a huge difference. So what is the cost to find C? Cost to find C is what? Yes?
N multiplications, right?
So the whole matrix C. I want all, I'm greedy. I want all of C.
Gives you that n squared times.
Yes. So it is n cubed multiplications and then n squared times n minus 1 additions. Okay. So if I look at that, it looks like matrix multiplication is an n cubed algorithm. How does that compare to polynomial evaluation? It's worse. But of course, we also have more terms. Right? If I have an n by n matrix, I have n squared elements in play. In a polynomial of degree n, I have only n plus 1. So I'm not surprised that it's more expensive. I have more things I need to do. Are you all sufficiently motivated that we want to calculate products of matrices? I saw some people say no, so later today I will motivate why we care about products of matrices. For now, assume I have given the most compelling speech you have ever heard about the importance of multiplying matrices. Later today, I will talk about applications of the Fibonacci numbers, matrices, and Las Vegas. And I will refer you to a nice video I made with some students at OIT a few years ago. But for now, you're all completely motivated that you want to do this. There is nothing more important in your life other than beating Amherst in figuring out how to do this more efficiently. Because that's what we do in this class. Okay? What's the real bottleneck? What's the real difficulty in this calculation? What's the real cost in the multiplication? So what's the cost? What's the difficulty? Yes?
Doing the dot product of that row and column.
So the dot product, so each row is costing me n multiplications. Is there any way to do a given row faster? Can you have a flash of insight and find a better way to take the dot product? Seems unlikely because you seem to have to somehow involve all of those numbers. The flash of insight that Strassen had was if you are trying to calculate a specific entry Cij, this may be the best thing you can do. But when we're trying to calculate the matrix C, we're trying to calculate all theCij's. And so maybe what we can do is we can maybe rearrange the calculations in such a way that we do some of the calculations multiple times. Well, if we have to do some of the calculations multiple times, we only need to do them once. We only pay for them once. Now, what's going to be the trade-off? Storage. Usually that is a good deal. And so if I really cared about you, I would have memorized this. I don't. And so if we had a better classroom and I could just pull it down the screen easily, I would do that. We don't. And so I'm going to define M1 as A11 plus A12, plus A22 times B11 plus B22. M2 is equal to A21 plus A22 times B11. Do you want me to continue, or do you want me to just say there are choices, and you can see them on the web? Okay, when I say, do you want me to do this or this, when you say yes, that's not a, I will continue. M3 is A11 B12 minus B22. I should have printed this out for someone to look at. M4 is equal to A22 times B21 minus B11. M5 is A11 plus A12 times B22. M6 is equal to A21 minus A11 B11 plus B12. How many more multiplications do you think, how many more terms do you think I have?
2.
Okay. If I have 2, I'm a bad professor. Why would 2 more terms be bad? And that would be n cubed. I have a 2 by 2 matrix. If I have 2 more terms, then I would have 8 multiplications. That's how many I started with. So I can't have 2 more multiplications, 2 more terms to define, or this is going to be a horrible lecture. What's the most I could have? 1. I actually do have 1 more. We have M7 is A12 minus A22 times B21 plus B22. Okay, so there we go. We have 7 terms here. What can you say about 7 versus 8? Yes. So theorem, 7 is strictly less than 8. Okay? What are the consequences of this? The consequences of this turn out to be enormous. So we actually get the following. C11 is M1 plus M4 minus M5 plus M7. C12 is M3 plus M5. C21 is M2 plus M4. And C22 is M1 minus M2 plus M3 plus M6. How many multiplications? So what is the number of multiplications? How many? How many multiplications? 7. How many additions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Does that match? Anybody get anything else? Oh, wait, did I skip this one? Maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, it's getting higher. All right, 18. 18 additions, 7 multiplications. The old way, what was the old cost? We had 8 multiplications, and how many additions did we have? 12. Each dot product took 3 additions. We had 4 dot products, that was 12. So here's the change. I will give you 1 less multiplication at a cost of 6 additions. Is that a good deal? Yes. Multiplication is far more expensive, especially if you have large numbers, than addition. This is a terrific trade. And in fact, what this tells us is this algorithm runs a lot faster. And you can try to figure out, how does this algorithm scale with n? What if you have an n by n matrix? It turns out the best choice for n is to be a perfect power of 2. And what you can then do is, if n is a perfect power of 2, let's say n equals a 4 by 4 matrix. You then write it as a bunch of 2 by 2 blocks. And then for the 2 by 2 blocks, you do matrix multiplication in blocks. And you keep iterating this method down. If you have an 8 by 8 matrix, you break it up into 4 by 4 blocks. And then when you multiply the 4 by 4 blocks, you consider them through 2 by 2 blocks. And you can iteratively save all this information. And the end result is you go from an n cubed cost to an n to the log of 2 base 7. Now, the log of 2 base 7, there's another way to write 3 that will look more closely related to the log of 2 base 7. How should I write 3?
Log base 2 of 8.
Log base 2 of 8. Excellent. So the log base 2 of 8. In terms of trying to figure out just how expensive something is. We've replaced the 8 with a 7. Does that look like we've made an accomplishment? No. Right? If you have not worked professionally in this subject, it's like, so you changed 8 to a 7. This was one of the greatest advances in algebra, in linear algebra in the 20th century. Because when n is huge, compare n to this to n to that. The Strassen algorithm is not the best possible. And again, there's always a question of how much should I go through in class? What is the fountain of all wisdom? Wikipedia. You go to Wikipedia, look up the Strassen algorithm. I'll post a link to that later. You can read more details about how you build this up. I want to just give you the main idea and see that we're saving a multiplication. So to try to get a sense of what happens as we keep propagating. This is the power. And so what's so wonderful about this is when n is very, very large, that power savings is enormous. Remember, what we did earlier in class was we went from an n squared algorithm, the brute force polynomial evaluation, to an order n algorithm. So if n was 1,000, rather than doing 1,000,000 operations, we did 1,000 operations. And you can begin to see now that a power savings here will have incredible consequences in terms of what ranges are accessible. Okay? So again, I'm trying to give you a flavor of what we're going to be doing in the class, trying to review linear algebra at the same time. Any questions about the stuff up to here? This just general idea. Do you think that this is hard to see? Yes. Do you think this is hard to prove? that this works? No, how would you prove it? Just multiply it out, right? There's a lot of things in mathematics, computer science, where it's very hard to come up with the answer. But once you have the answer, it's actually very easy to check and see if the answer is right. And so for those of you, how many of you are in CS? Okay, how many of you have done stuff like this where you have problems that are very hard to evaluate? They have names for these classes of problems where it can take a long time to solve, but it can take a very short time to determine if your answer is correct. So a lot of times you might want to know, do I have a valid schedule? Do I have a path that hits each vertex exactly once? Well, I'm walking through my graph and you give me a path. I just see, do I go through each vertex at least once? And do I maybe never go over an edge twice? There's a lot of problems where it's very easy to check and see if the answer you have meets all your desired properties. But it's very hard to find that answer. This is a wonderful example of I can easily check and see if this is correct. All right, so I wanted to talk to you about why we might care about matrices. So for me, one of the biggest applications of matrices is in eigenvalues and eigenvectors. So eigenvalues, eigenvectors. And in fact, for a lot of these, you can oftentimes avoid the cost of doing painful multiplications of matrices. So, this is A of V is lambda of V. So in general, when you apply a matrix to a vector, normally it changes the direction and normally it changes the magnitude. If it only changes the magnitude, then we're lucky and we say this is an eigenvector and lambda is an eigenvalue. Okay? We normally assume V is not 0, because if V were the 0 vector, then it would have any possible eigenvalue. Why do we care about eigenvalues and eigenvectors? The matrices, the behavior is very nice with respect to the eigenvectors. And if we can write an arbitrary point in terms of the eigenvectors, we can then understand its behavior very nicely. So for instance, imagine we can write V as C1 V1 plus Cn Vn, with the Vi are the eigenvectors. Then if I apply a n times, well, no, let's do m times. If I apply a m times, applying a matrix is linear. A to the m applied to the sum is the sum of a to the m applied to each term. Also, because it's linear, if I apply am to c1 v1, that's the same as c1 times am to the v1. Well, if I apply am to the v1, if I apply it once, I get lambda 1 v1. If I apply it twice, I get lambda 1 squared v1. If I apply it 3 times, lambda 1 cubed v1. And so I'll get just c1 lambda 1 to the m v1 plus cn lambda n to the m vn. So here's one nice reason why we can care about matrices and why we might want to take high powers. So one way is to compute am directly. Another way is to take the eigenvalue expansion. Depending on your problem, one way might be easier than the other. The difficulty here is I need to find the eigenvalues and the eigenvectors. Who knows how to find eigenvalues and eigenvectors? Yes?
Well, the eigenvalues, you can plug in diagonal minus lambda and then set the determinant equals 0.
Okay, determinant of a minus lambda I equals 0. So if this was a theoretical math class, I would say great answer. But this is not a theoretical math class. What's the problem with this? I'm sorry, we have to? Finding a determinant could be expensive. Maybe there's a fast way to do determinant, but finding the determinant cost could be expensive. What else?
It's one of those problems that's easy to check but hard to solve.
Yeah, to actually find this, if A is 1,000 by 1,000 matrix, you're now going to write down a polynomial, and try to find all the roots. We can't even do 5 polynomial of degree 5. So again, theoretically, we can be very happy by saying, oh, well, this is how you find the eigenvalues and eigenvectors. And we can prove theorems such as the spectral theorem for real symmetric matrices that says if your matrix is real symmetric, it has an expansion like this. Oh, you mean you actually want me to find it and do something with it? So in terms of actually doing something, it could be a lot harder. So it's nice to maybe be able to calculate high powers of a matrix. Let me give you a quick last application of where you might use something like this. And so I'm going to quickly tie it to the Fibonacci numbers. And for those of you who have done research with me, I will use the standard definition of the Fibonacci numbers, not my preferred definition. And I see some nods. So f0 is 0, f1 is 1, fn plus 1 is fn plus fn minus 1. So these are the Fibonacci numbers. 0, 1, 1, 2, 3, 5, 8, 13, ... And again, if you have any issues with how the class is going, I'm still trying to figure out what's the best way to structure this, that's the password you use to email me anonymously. Okay? Let's calculate the Fibonacci numbers in closed form. Right? If I want the 1000th Fibonacci number, is that a hard problem or an easy problem, theoretically? Easy. Just keep walking down. If I want the 1,000,000th Fibonacci number, easy, right? If I actually wanted to calculate and do the calculation, easy or hard? And I would have to walk through every single Fibonacci number down the line to get there. What I'm going to show you is a way to jump to whichever Fibonacci number you want by using matrices. So let's let Vn equal Fn, Fn minus 1, Vn plus 1 will be Fn plus 1, Fn. So Vn plus 1, I claim, is 1, 1, 0, 1. And the reason is this is telling me Fn plus 1, Fn is 1, 1, 0, 1 of Fn, Fn minus 1 is Fn plus Fn minus 1. Oh, sorry, it's the other way around. 1, 0. So here's a way to march down the Fibonacci numbers. So if this vector is 1, 1, 1, 0 times Vn, let's call that AVn. So instead of saying it's AVn, it's A squared. It's A squared what? So what would it be? Vn plus 1 is A times Vn. It's the same as A squared times Vn minus 1. Because Vn, I just use this relation. I replace n with n minus 1. And I would get Vn is A times Vn minus 1. So this is the same as A squared times Vn minus 1. It's the same as what? What would be the next thing? A cubed. And it goes all the way down to A to the n times V1. And the reason I know it goes down to n is 1 times n is n plus 1, 1 plus n is n plus 1, 2 plus n minus 1 is n plus 1. The sum of this number and the index down here adds up to n plus 1. So if I go all the way down to V1, I've got to have an n over here. So if I want to calculate the Fibonacci numbers, here is a way to jump to wherever I want if I can calculate high powers of this matrix. So it all comes down to, can I diagonalize, for instance, a 2 by 2 matrix? Can I calculate its eigenvalues, eigenvectors? I can, and this actually leads to a beautiful formula. This is one of my favorite formulas in mathematics. It's Benet's formula. Fn is 1 over root 5, 1 plus root 5 over 2 to the n, minus 1 over root 5, 1 minus root 5 over 2 to the n. This is a very strange formula. What property can you tell me about the Fibonacci numbers? What kind of numbers are they? Integers. If there was a police lineup of numbers, and you were asked by the cops to identify the integer, does this look like an integer? Not even close. You've got square roots, you've got divisions, but at the end of the day, it comes out as an integer. And this allows you to jump to whichever Fibonacci number you want without calculating any of the intermediate steps. And there's a lot more we can say with this. We're out of time. This is a good natural stopping point for the first real lecture. So again, this is my first time teaching this as a pre-core 300. There's a lot of different things to emphasize. The danger of having a class as large as this is there is a very diverse audience in terms of what you want to get out of this. I know this from the emails I've received, and what your backgrounds are. So it'll be a much better experience for all of us if you give me some feedback. Either email me directly or email me anonymously. Tell me, is this working for you? Is this interesting? And again, I'm trying to be a little slow in the material so that you have time to get caught up with your linear algebra, make sure that's all good, and read ahead in the book. Okay.